Okay, so new unit is going to be about solving systems. We start off with just solving linear systems. Today will be 100% review, 100% review. Tomorrow, not so much. Tomorrow we'll expand this a little bit and it'll start to be definitely some new stuff, but today is going to be review. So first of all, let's just kind of remind ourselves what's going on here. Let's talk about and remind ourselves about what it means to be a solution. What's it mean? What does it mean to be a solution of a linear equation? Like, for example, how could we know if the point 36 is a solution of that equation, and what does that mean? What do you think, Cameron? Okay, right, so if it makes the equation true. Now, how do we say that in math? What is it, how would we say, what's our more efficient, yeah, okay, if it satisfies the equation, if the point satisfies the equation. Now, earbuds need to be away, please. If I plug those in, it makes it true, then that's a point, that ordered pair satisfies the equation. What's that mean about the graph? Because this corresponds to a point, right? So what's that tell me about the graph? Okay, right, so that's a point then that would be on the line, right? So if we plug in 3, 6, does it work, by the way, if I plug in x equals 3, y equals 6? It does work, doesn't it? Yeah. So, I thought I had, there we go. Right, so we can see that that point sits on the equation of the line, right? How about this other point, 6, 4? That works also, doesn't it? Okay. So both of these points are solutions of the linear equation because they sit on the line. Some point that doesn't would not be, right? Okay. Now, if we advance this a little bit and we talk about, instead of just a single equation, if we talk about a system of equations, all that means in math, a system of equations just means what it sounds like. It's just multiple equations gathered together, right? So now we've got a system of 2 equations. So in order to be a solution of the system, then any ordered pair would have to satisfy all of the equations in that system, right? Because now there's more than one equation contained in the system. So you guys do a little mental math here and check. Is the ordered pair 3, 6 a solution of the system? We already know it works in the purple line. Does it work in the orange line? It does, doesn't it? Yeah, okay. So then predict what that's going to look like in terms of a graph. I've got these 2 lines. Are those, can you verify for me, are those different lines? They are, right? Definitely different lines, right? If I put those in slope-intercept form, I would get different slopes, wouldn't I? So what does that mean? If the point 36 is a solution of both lines and therefore a solution of the system, can you predict what the graph is going to look like? Say it again. Okay, yeah, so it's got to be a point that sits on both lines. And what's the only way that that could happen? Well, okay, it's not the only way, but in this case it's the way, because I have different lines. The only way lines with different slopes could share a solution would be if they crossed, right? How about the point 6, 4? That was a solution of the purple line. Is it going to be a solution of the orange line? You don't even really have to think about it or to check it, do you? If you think about this logically. If these 2 lines, how many points do these 2 lines cross at if they have different slopes? 1, right? They can only cross at 1 point. And if that point has an ordered pair 3, 6, then the point 6, 4 can't work. It can be a point on the purple line, but it cannot be a point on the orange line because they only share 1 line. And we could check it. We could plug it in and just check. But here's what it looks like. Right, so again, we see that, yeah, both the green and the red points sit on the purple line, but only the green point sits on both lines. So that's the solution of the system, okay? So what are the possible ways then, if we have a system of two linear equations, we can think about this graphically. What are the possible ways that they could interact? Well, we already saw something like this, right, where they share a single solution. Of course, it's possible that the lines could be parallel, in which case there's no solution, right? They never cross. Or they could end up being the same line, in which case there's an infinite number of solutions because every point on each line is a solution, right? So how do we describe these? A little bit of terminology. This is probably new. I bet you haven't used this vocabulary yet. So we say a system is consistent if it has at least one solution, and it's inconsistent if it has no solutions. So parallel lines, that would be an inconsistent system, but one solution or overlapping lines would both be situations that we would call consistent because they each have at least one solution, right? So that's one way we characterize systems, is whether they're consistent or inconsistent. And the other way is whether they're dependent or independent. Independent equations are just equations that are different, right? Dependent equations are equations that are the same. So they, in this case, they correspond to the same line. So we would say that both the situation where we have a single solution, one intersection, that's created by two different lines. So those are independent equations. And also, two parallel lines are clearly independent. They're different lines. So we combine both of those things. And how would we describe then, like for example, this situation over here where we have a single solution using both adjectives? What would that be? It's going to be consistent, independent, right? See what I'm saying? So this is the one that's a consistent, independent system. How about this one? Inconsistent, independent, yeah, right. And how about this one? Consistent, dependent, yeah, right, okay. All right, so now let's get down to nitty-gritty. Let's talk about how we solve these systems algebraically. First way we can do it is using the substitution method. Give me a 1 to 5 on using substitution to solve a linear system. How well do you remember this? Okay, we're all across the board here. We'll review this. So in a nutshell, solving a system, whether it's a linear system or a more complicated system, solving by substitution just means this. We're going to solve for one variable in one of the equations and substitute into the other equation. One of the rules that we have when we talk about a system, and we'll talk more about this later, but if I have a system that involves two different variables, x and y, in order for us to be able to solve that system, we always have to have at least as many independent equations as we have variables. So if I've got two variables, in order to solve for the values of both of those variables, I need to have at least two equations, right? And that probably makes sense if you think about our graphs, right? Because our graphs, if we go back and look at these, there are an infinite number of points that sit on that purple line, right? There's not just one solution, there's an infinite number of solutions. So I can't just pin it down to one. But if I've got two equations, now there's only one point that sits on both lines. And so because I've got two equations, I can solve for the values of both of those variables in the system. There's only one place that's going to satisfy both equations. But if I eliminate the orange line, now there's an infinite number of points that satisfy just that single equation. Every point on the line is going to satisfy that purple equation. So that's not enough information. Just having if I've got two variables, x and y, and I want to solve for both of them, a single equation is not enough. There's an infinite number of possibilities. Okay, so then our goal with substitution is we've got two equations. We want to solve for both of those. I've got two variables. The goal here is to degrade that system of two equations into a single equation that's only got one variable in it, which is easy to solve, right? And the way we do that, again, is by solving for a variable in one equation and substituting into the other. And what that ends up doing is eliminating a variable, and we'll see that. As we go through step by step, we'll see that happen. So let's take an example. So what about this system right here? Okay, this is one, we'll solve this by substitution. Okay, so what do we do first? Well, we're going to solve one of the equations for one of its variables. Well, all our work's done for that first step here. Both of these linear equations are already solved for y. In other words, y is isolated in both of them. So we can just check this one off immediately. Now, when we're doing this process of solving a linear equation by substitution, as soon as we solve one of the equations for a variable, so we isolate a variable in one of the equations, immediately put a box around that equation. We'll just pick, in this case, it doesn't matter. We can pick either one. We'll just pick the bottom one arbitrarily. That's our substitution equation, and we're always going to come back to that. So as soon as you isolate a variable, put a box around it, and then make your substitution. So step 2 is we're going to substitute the expression into the, this isolated variable. We're going to plug that expression into the other equation. So we know in the bottom equation that y is equal to x minus 9. Now we're going to make that substitution into the top equation. Okay? What's that give us if we make that substitution then? What equation do we get? So, okay, so now we get x minus 9, because that's what y has become, is equal to negative 7x minus 1. Okay, you see the advantage, right? By making that substitution, we traded that single y for an expression with x's in it, and now my equation, my top equation, only has one variable, so I can solve it, right? If I have a single variable, all I need is a single equation to find the value of that variable, which I have. And this is a piece of cake. What am I going to do here real quick? Push the x's where? To the left. Okay, so if I add 7x, I'm going to get 8x. Push the numbers to the right. Good. And we're going to get 8. So what's my value of x? Good. Okay, so x equals 1. So we're halfway there, right? We're actually probably more than halfway there. We know the value of x. Now, how am I going to find the value of y? Plug in where? Yeah, do you see why we boxed that equation now? In this case, it's pretty easy because the equations were already isolated for y. We already solved them for y, but in a lot of these cases, we won't. We'll start off with equations where y is not isolated. We'll go through the process of isolating y in one equation, and then the boxed equation is our substitution equation, right? That's the one where we can immediately just go plug right back into that boxed equation because it's easy to find the value of y. Y is already isolated, okay? So that's why we always want to box that substitution equation. If I plug x in, what do I get for y? Yeah, y equals 1 minus 9, which is negative 8. And now I've got both parts, both parts of the equation, the values of both x and y. So how would I write my solution? As an ordered pair, yeah. Okay, so then this is just going to give us the ordered pair 1, negative 8. Okay, I have to write it as an ordered pair instead of just a number because my system involves two variables. So I have to give the values of both of those two variables in my solution. Okay. What if I had a system, which we'll look at tomorrow, which involves three variables like x and y and z? How many equations would I need to solve a system with x and y and z? I would need 3 equations. Yeah, I couldn't do it with 2. 2 would be insufficient. I'd need to have 3. And when I solve that system, how would I write my answer? Not as an ordered pair. What would it be? How many numbers would I have to include? I'd have to include 3. It'd be an ordered triple. Yeah, I have to include numbers for x and y and z. Okay, but we're not there yet. Okay, and then we could, of course, check our solution by plugging into the original system. Now, here's the thing. How many of those equations do I have to plug my solution into to check? Just one? If I plug into just one, that doesn't verify that it's a solution of the system, though, right? Because to be a solution of the system, My ordered pair has to satisfy both of the equations, so I would have to plug it into all of the equations in the original system to check to see if it actually is a solution. Now I could use Desmos to do that, right? That's not a big deal. How could I, remind me how I would do that? How do I use Desmos? We've been doing this all year. Desmos Scientific, I don't need Desmos graphing. What could I do to check my ordered pair 1, -8? I mean, I'd take that equation, right? Let's actually go through this. Let's go through the Desmos, because I'm going to show you, I think maybe I'll show you a little extra trick here on this one. Okay, so we could, well, if I want to do this, remember, I could always just plug in numbers, right? I could just go up here and plug in, what's my ordered pair again? 1, -8. I mean, I could just literally plug in -8 and 1 and just see if it works. Or I could do something like this. The left side is already y, so I know the left side has to be -8, right? In both of those equations, the y coordinate of my solution was -8. I just have to check to see if the right side gives me -8. And a really easy way to do that would be to say something like f of x equals -7x minus 1, and then just try f of -1. Oops, was it 1 or negative? It was 1, okay. F of 1, yeah, there we go, and I get -8. It works. And then I could just either go up and change this or make g of x. Like I could go up here and just alter this for the second equation and just change f of x to x minus 9, and it adjusts and it's still -8, right? So it works, okay? Give me 1 to 5 so far. I'm going pretty fast because I'm reviewing, but we all good with this? Okay. All right. Okay, so if I want to use the substitution method here, be smart about this, because that's a lot of what we do in here is not just being able to do the math, but being strategic about doing the math. What would you do? Because there's definitely a best way to do this using substitution. Which variable would you isolate? In which equation? The bottom equation, right? When we're using substitution, remember our first step is to isolate one of the variables in one of the equations. We would always want to do that in the easiest possible way. So we would choose one of the variables that has a coefficient of 1 or -1, so it's super easy to isolate, right? All I've got to do to isolate that y is just subtract the 7x to the other side. Why would, for example, y in the top equation be not a great idea? Say it again. And what does that end up, if I solve for y, it's going to look kind of ugly. What's going to end up happening if I solve for y in the top equation? I'm going to get a bunch of fractions. You really feel like substituting fractions? Probably not, right? And what we ultimately decide here is that we're really only use substitution when it's easy to do. If I don't have a variable that I can isolate without creating fractions, I'm not even going to use substitution. I'm going to move on to the other method that we'll talk about soon. So substitution, it's fine to use, and where it's really easy to use if it's easy to use, if there's a variable that's really easy to isolate without creating fractions. Okay, so let's go through this process. First step is isolate a variable. You guys correctly identified the variable I want to isolate. That's y. If I isolate y, I just get -7x plus 22. Okay, what do I have to do now? Plug that in. Okay, but I forgot to do something though that I always do whenever I isolate a variable. I box it, yeah. Always going to put a box around it because then it's easy to find when I need to, and I'm going to need to. So I box it, And then I heard the next step correctly. I'm going to take this value of y and I'm going to plug it into the other equation, of course. I can't plug it into the same equation. So if I plug it into that top equation, what am I going to get? Well, I get 6x minus 5 times the quantity, negative 7x plus 22, right? Because this is where we're going to plug in that value of y. So I've noticed that sometimes people are forgetting to put, in their mind they're doing it, but when I look at work on tests and things, people sometimes forget to put parentheses around stuff that's being substituted like this. Everybody sees why I absolutely have to have them, right? If I didn't have the parentheses, that would be a very confusing statement. Negative 5 minus 7x, that wouldn't make any sense. And even if that were a positive number, it would look like the first term is the only one that's being multiplied by negative 5. I have to have the parentheses there. Anytime I make a substitution of a quantity that's more than one term, it has to be included in parentheses. And it's best to just always put it in parentheses. Okay, and then that's just my y value, so then that's all equal to 22. Okay, I can solve that equation because it's only got one variable, right? Let's say it again. Oh, you're right. I put in the wrong number, didn't I? Top equation, right? So it's negative 28. Good eye. All right. So then we solve this. That's a piece of cake. You guys can do this in your sleep. So we distribute the negative 5. We get 6x, what, plus 35 minus 110. Did I mess up here? Oh, x, right, x, you're right. 110 equals negative 28. You better be, I'm making lots of mistakes. You better check my work as I go here. 5x, 41x. Add the 110 to that side. What do I get? 82. Good. So what's x? 2. If I divide both sides by 41, I get x equal 2. Am I done? Halfway there, right? I got the x coordinate of the point of intersection, but now I need the y coordinate, I need the other part of the ordered pair. Where do I go? The box. See, now I go right back to the box. How easy is that? There we go. If I plug into the box, we get y equals negative 7 times 2 plus 22. Well, what is that? Negative 14 plus 22? 8. Okay, and we got it, right? We got both parts. X equals 2, y equals 8. Then we're done. Okay, give me thumbs. How we doing? Okay. Okay, so what about this one? Is substitution a good idea? Terrible idea, right? Terrible idea because there's no variable that can be isolated without creating fractions. So we really don't want to use substitution here. Okay, we want to use something else. We want to use the eliminate, is that what you guys called it, the elimination method, or did you call it linear combination? Elimination? Okay. So the elimination method. Okay, so how do we do the elimination method? Well, the elimination method is, I think ultimately you're going to find this is the one that you probably use this one 90% of the time. It's just easier. It's just easier to do the math. And here's the real advantage. You won't see it so much now, but you'll see it very, very soon. When we solve systems that involve more than one variable, or more than two variables, linear systems with 3 variables or 4 variables or 7 variables, something like that, this would be by far the easiest way to organize your work. Okay, and what we're going to end up doing, we're going to do this a little bit. We're going to go through the normal Algebra 2 stuff, this unit, and then at the end of the year we're going to loop back and we're going to come back and revisit linear systems, and I'm going to show you guys in the honors class, I'm going to show you how to solve linear systems using matrices. So you could start to see how you could solve like bigger linear systems. Linear algebra, I mean, I know you think of solving linear equations as being a really simple thing, and it is. Linear equations in one variable are just really, really simple. But when you're solving linear systems that involve many variables, it gets kind of complicated, and it becomes a really powerful tool. I'd say that the two tools that you use the most in advanced math, if you're applying the math, if you're doing physics or engineering, something like that, the two tools that you use by far the most that just do the lion's share of the work are linear algebra, believe it or not, being able to efficiently solve really big linear systems using matrices. And then the other one is calculus. The calculus, which takes years and years and years to kind of develop calculus to the point where you're able to use that. But after you've gone through a couple of years of college calculus, maybe 3 years of college calculus, then you start to become really good at solving differential equations, and that's the other big tool that we use. Okay, but this is you're seeing the beginnings of a really, really powerful thing in math. So let's start with a really simple example. We'll just look at a system with two variables, and then later on we'll extrapolate this into some bigger systems. So how do we do this with elimination? Well, we always want to write the equations in standard form, where we have the x term and the y term are on the left side and the constants on the right side, and ideally we'd like those to be integers if possible. If there will be some cases where they can't be integers, but we're not really going to deal with those this year, where those are, for example, irrational coefficients, but that's for later. We want to do this to both of the equations in the system, and then our goal is we want to line them up in such a way that we could multiply both sides of one equation, or maybe even both equations, so that either the coefficients of x are opposites or the coefficients of y are opposites. So when we add those linear equations together, one of the variables falls out, drops away, it cancels. Okay, and then once we do that, we're left with an equation with only a single variable, which we can solve and substitute back into one of the original equations to find the other variable. That's a lot of words, too many words. Let's just do an example to kind of illustrate how this works, and I think you'll remember. So here's a linear system. Is it set up right now so that if I add those equations vertically, one of the equations is canceled? Like if I just add these two equations up, and literally what I mean by that is if I just put a bar under this and add that bottom equation, would any of the variables cancel? Well, they wouldn't originally though, would they? Right? Because I'm going to get x plus x is 2x, 7y minus y is 6y, and then I get some number on the other side. So I'd end up with a new equation that still involves two variables. So I didn't accomplish anything, because my goal is to get an equation with only one variable in it so I can solve for that variable. Right? Anytime I have a single equation with one variable, I can theoretically solve for that variable. Right? At least if they're linear equations, we always can. Right? There are some types of equations where we may not be able to solve it, but those are not linear equations. Those are very complicated functions other than lines, right? So it's not quite prepared for us to eliminate a variable yet by adding these equations up. I have to do something to at least one of those equations so that either the x's or the y's will cancel. Any ideas? Say it again. Okay, yeah, I could multiply, just to say the bottom equation, for example, by -1. If I distributed a -1 through the bottom equation, let's see what happens. Now, here's the way I show this. This is kind of my own thing, but I think it's pretty good. I use arrows. If you just have a straight arrow with no bubble in the middle, that means you're just going to leave that equation unchanged. So this top one, I'll tell you what, I'm going to move them clear over here too. These are going to be some long arrows. So we have a little more room to do the work. Top equation remains unchanged. That one's going to be x plus 7y equals 17. What am I going to multiply the bottom one by again? -1. Okay, if I distribute a -1 all the way through the bottom equation, what do we get? Plus y equals +7. Okay, now you see the advantage of this, right? Now we can eliminate x. When I add these equations up, the x's cancel, and I end up with 8y equals 24. Okay, so you might be wondering, like, what allows us to do that? How can we just add equations together? There's a couple ways to justify this, to think about it. One of them is, if the left side of an equation is equal to the right side, what's my rule for solve? If I have an equation, what are my rules of equality? They just say I can either multiply both sides by the same thing, or I could add the same thing to both sides, and the equation should stay an equation. As long as the way we always kind of phrase it is, as long as I treat both sides equally, it's going to stay an equation, right? Where the left side and the right side will remain equal. So if we know that in the bottom equation, I know that -x plus y is equal to 7, those things are equal, then I could add those to the top equation, and I'm adding equal things to both sides of the equation, right? So it should stay an equation because the bottom equation tells me they're equal, right? Give me thumbs on that concept. Does that make sense? Okay, there's a more potent way of saying this that we'll come back to. It's called the principle of linear superposition. I'm actually even going to write that down because it's so important in math and physics. When you study physics and you study, for example, light or radio waves or any kind of electromagnetic wave, the way that we do the physics of understanding the way waves interact is with this principle. It relies completely on this. And what it means, for example, and I don't want to get too far in the weeds with this, but what would happen, you probably have this experience, if you're in a boat and you have a big wave coming from one direction and a big wave coming from the other direction. When those two waves meet, you're going to get an extra high wave, right? Because the waves add up. So you get however high this wave was and this wave was, when they meet, you're going to get tossed up double that height, right? So the waves combine linearly, right? Their amplitudes add. But also what happens, if one of the peaks of this wave combines with one of the troughs of this wave, then nothing will happen, right? They'll completely cancel each other out. And so that's that principle of linear superposition where waves of any kind, could be light waves, sound waves, any kind of wave in physics, they behave in a way that's exactly like the math we're doing right here. Is it easy to connect the math to that? Well, not exactly. You have to add some trig in there, but I just want you to have kind of a glimpse looking forward as to, why is this stuff, how could this possibly be important? That's how, right? That's one example. When you're trying to see how waves interact, they interact in this way exactly. You can just add up those linear equations to create a new linear equation that describes the situation. And so what we say with the principle of linear superposition is this. If I have two equations in a system and I add those equations up, then the new equation that I get will be consistent with that system. Any solution of this new equation will also be a solution of the previous equations. Okay, so at a theoretical level, that's why we're able to do this. Any new equation we create by linearly combining, by adding these original equations, is still going to work in the original system, right? Which is to our advantage, because this is an easy equation to solve. What is the solution of that simple equation? Y equals 3. So this is a completely different equation than what we started with, right? But we end up with the solution y equals 3, which we know is going to work in our original system, okay? Because of that principle of linear superposition. So now what am I going to do? Substitute into either one of the original equations. Just pick the easiest one. Probably the bottom one, right? Smaller coefficients. If I plug y equals 3 back into this bottom equation, what do we get? X minus 3 equals negative 7. So what's x equal to? Negative 4. Okay, and then we've got the ordered pair, negative 4, 3. Okay, give me 1 to 5. Is this all ringing a bell? Remember doing this stuff? Okay. Give me a little, I need feedback from everybody. Give me, you can be sneaky about it. Give me a 1 to 5. I need to know where we are on this. Are we, okay? Let's do some more examples. The right one, yeah. Okay, so walk me through this one. This time we're gonna use elimination, not substitution. So the first thing to do would be to ask yourself, which variable is gonna be easier to eliminate, x or y? And what would be the criteria? What would make, like in this case, what do you think is the easiest variable to eliminate? We can have a discussion. I'm hearing some x. Anybody pick y? Okay, nobody's picking y. Okay, I agree with you, it's x. Picking y would be a little bit tough because I would have to multiply both equations by something to get opposite coefficients of y. Everybody agree? X is simpler because I only have to multiply the bottom equation. The top equation I can just leave unchanged. So the top equation stays as it is. What am I going to multiply the bottom equation by? 4? Negative 4, right? Because now you might be, this might be slightly different than what you've done in the past. In the past, have you guys subtracted vertically? Maybe, possibly. We don't want to do that. We want to always add vertically, so we want to make them opposites. So we're going to multiply the bottom equation by negative 4. If I distribute a negative 4 all the way through, what do we get? Negative 4x minus 20y equals 16. Okay? So now we can eliminate, now we can eliminate the x's, right, when we add vertically. Negative 9y plus negative 20y is negative 29y. That should be negative 16, right? Yeah. Negative 29y and negative 42 plus negative 16, negative 58. So what's y? 2. If I divide each side by negative 29, we get y equals 2. Where am I, question? Okay. Where am I gonna plug that y? Top or bottom equation probably? Bottom would be easier, wouldn't it? Okay, so we'll plug this guy in right here. And then this bottom equation is going to become x plus 5 times 2 equals 4. So what's x? Negative 6? Yeah. Okay. How's that doing? Is that helping a little bit? Okay. So we get the ordered pair negative 6, 2. Okay. Okay, what about one like this? Here, I'll make that a little bigger. Okay, look at that one for a second. It always pays to take a second and think about it before you jump in. Which variable would be maybe, we can have a discussion here. Which variable would probably be easier to eliminate and why? And you can make arguments for either one. Anybody say why? No whys? I would agree. I'd say x. What's your reasoning? Why x? What do you think, Cade? Okay, so you're multiplying the bottom by 5 and the top by, well, bottom by 5 and 2?
Bottom by 5 and top by 2.
Okay, one of those would have to be negative, right? Yeah. So, but if I think about the size of that, I'm multiplying by 5 and 2. The product of those two things is 10, right? So overall, I'm multiplying by 10. I'm just splitting it between the two equations. What about for y's? I'm multiplying by like 7 and negative 3. 7 times 3 is 21, so the number is bigger, right? That means I'm going to end up with bigger coefficients if I eliminate the y's, and it just makes the math a little more cumbersome if I've got bigger coefficients. We'd rather be dealing with simpler equations with smaller coefficients. Okay, give me thumbs on that concept. Does that make sense? So we want to multiply by the smallest things possible if we can. Okay? All right, so then we're going to multiply, we said, by 2. And by, what's the bottom going to be? Negative 5. There we go. So what's the top equation become if I distribute a 2? 10x plus 6y equals negative 14. Okay, if I distribute negative 5 in the bottom, negative 10x minus 35y equals negative 15. There we go. And that's good because the x's cancel. I think we've had the x's cancel every time. Do we have to make the x's cancel? No, it doesn't matter. Doesn't matter. We can cancel either variable. So we end up with, what, negative 29y equals negative 29. So what's y? 1. And then, yeah, I mean, this is getting a little bit redundant, right? Then we can just plug that y in there, and we get 2x plus 7 times 1 equals 3. Go ahead and solve that for x. What do we get? Negative 2, right? I'm going to subtract 7 and then divide by 2. So there's my ordered pair. Okay, now, 1 to 5. Give me a little feedback here. How are we doing on this now? Okay, good. We're climbing the ladder. That's good. Okay, let's just try a couple more. And these are important ones, and you'll see why. Okay, how about this one? What do you think? What would be we have to eliminate a variable. Which one would be easiest? X maybe? Yeah. Okay, so what are we going to multiply top equation by? By 3. There we go. Okay. Top one by 3. Bottom one by negative 2. Okay, that's a 3. So what's that give us on the top? Equals, what's 3 times 30? 90. What's 3 times 8? So what do we get? 114. There you go. Okay, on the bottom, what do I get? Negative 6x. Okay, so now what happens when I combine those? Yeah, look at that. We get the solution 0 equals 0. Okay, what do you think's going on here? Yeah, okay. How did we always interpret that in the past? The math gods are telling us something important. If the variables drop away and we get a true equation, what did that always mean? It means the solutions, there are an infinite number of solutions. What's the only way that could happen here? If the lines are the same line. There we go. So this is same line. Okay? So what would we call it? What kind of system would that be? Do you remember? Consistent or inconsistent? Consistent, dependent or independent? There you go. Consistent, dependent system. Okay? Okay, good. One more. One more for today. I think then we're, yeah. One more and then I'll probably just turn you, when we'll talk about the last one, I'll turn you loose. Okay, how about this one? What am I going to eliminate here? Y. I agree. Top equation stays the same. Bottom one I multiply by what? Negative 3. Okay, top equation stayed the same. 6x plus 3y equals 7. What do I get in the bottom equation? Okay, so you probably predicted what was going to happen here, right? Okay, so right, so they're going to be parallel, aren't they? We end up with everything cancels on the left, so I get 0. On the right side, we get 22. Okay, so parallel lines, how come? How is that consistent with what we did before? What did we always say? What are the math gods telling us? If the variables drop out and we get a false statement, that means no solution, which means no intersection, which means what kind of lines? Parallel lines. So is that going to be consistent or inconsistent? Inconsistent. There you go. Inconsistent, independent. Okay, so we won't even do this last one, but I want to know, what would you do? Then I'll turn you loose to work on this stuff. Because that looks pretty ugly. Yeah, okay, let's clear fractions, right? Because we don't want to be dealing with all these fractions. We want these equations in standard form to have integer coefficients, right? So what would I distribute through the top equation? No, 30, right? I'm clearing fractions. So I'm going to multiply the top one by 30. What's that going to give me in the top? 30 over 6 reduces to 5 times 7, 35x. 30 over 5 reduces to times 9. Okay. And on the other side? Negative 60. Okay, on the bottom, what am I going to multiply by? Yeah, 60, right? Smallest number that both 12 and 10 divide into is 60. Okay, anyway, you got the idea. Assignment's up there. Have at it.